Okay, thank you very much for attending this session on Introduction to Aerospace Systems Modeling in GT Suite. And so let's first begin by just explaining a few common challenges we see in aerospace simulation. So there are a few key challenges. There are actually many that engineers are faced with when they simulate aerospace systems, but there's a few of them just listed below where, oftentimes, developing these systems is very expensive. Physical testing is costly, and it takes time to iterate to find the optimal design. And then furthermore, there are often challenges that occur during the design, and you want to be able to identify any problems early enough so that they don't bite you later on in the design process. And so we believe that multi-physics simulation can address these challenges. Now, when you talk about the realm of multi-physics simulation and the fidelity levels that are available for users, there's a spectrum of tools that are out there, ranging from the far left side here, which involves things like back-of-the-envelope hand calculations to Excel Visual Basic macros, some of them actually very sophisticated, and even to 0D type models of a given system. And typically those run on the order of seconds or so. And then you've got the opposite end of the spectrum here where you're looking at a detailed design and looking at it either in 3D with finite element analysis for structural or thermal problems, or doing 3D CFD. And when you're especially integrating these together, this can take days or weeks to find an answer for just a single operating point. Now, we like to think that the GT Suite simulation software can span this spectrum from very simplified fidelity modeling that allows models to run on the order of seconds to analyzing components pretty deeply to gain further insight into particular component analysis and surrounding these components in an entire system to do full system modeling. And that typically takes on the order of minutes and maybe sometimes hours at the most. But we also have a blend or fusion, if you will, of 3D capabilities as well. And we're going to talk to some of those points later today. But in terms of how GT Suite slots in the realm of CAE simulation for aerospace systems, it really can span both ends of the spectrum. A little bit about GT Suite. Actually, our company name is called Gamma Technologies, and our headquarters are outside of Chicago in a western suburb called Westmont. And we were founded over 25 years ago, back in 1994, and our business is focused exclusively on simulation software, research and development of a tool called GT Suite. Now, GT Suite is a transient multi-physics tool, and we'll get into a little more about what that means in a minute. And up till today, we have over 700 organizations around the world using our tool. And because it's a worldwide usage of the tool, we have world-class support at a variety of our offices, whether it's at our headquarters here outside of Chicago, where I'm speaking to you from, or from our local European office in Stuttgart, Germany, or a relatively new office that is in Pune, India as well. And then we also have our representatives at IDAJ that support our Asian clients in Japan, China, Korea, and so on. Now, when we talk about the world of aircraft simulation, there are many different subsystems that could be investigated for virtual analysis. And if we kind of start at the top here and work our way around, this ranges from environmental control systems and cabin comfort to de-icing. And then in terms of the power plant type simulation, the investigations could include detailed analysis for turbofans, turbojets, and turboprop systems, as well as IC engine propulsion, or even fuel cells and battery type of systems as well. And then for fuel related to standard jet fuels and so forth, fuel systems and 3D fuel tanks can be examined with simulation as well. And also there are systems like landing gear and hydraulics and braking to worry about on aircraft and so forth. And so these systems also need to be investigated, and there are avenues to explore that in CAE simulation and also in GT Suite. And then also to round it out here, more on the electrical side and flight controls aspects, and also life support, OBOGs and so forth. And also with the trend more towards electrification, batteries come into play as well. In terms of spacecraft, there are a variety of things that can be studied in GT Suite, whether it's a thermal fluid type problem where you have interaction between a fluid system, let's say a propellant feed line system leading to some thrusters. That can be integrated with a thermal structure and solving all three modes of heat transfer, whether it be radiation or convection or conduction. And this analysis can be fully transient to investigate either steady state or actual transient long time scale events or short time scale events to study things like water hammer. Now, in terms of fluid modeling, oftentimes fluids for space propulsion systems can be cryogenic and two-phase capable. And so with this, we rely on our backbone referring to NIST RefProp database for the detailed fluid thermodynamic properties. Now, there's also other things that you can do with GT Suite. It's a fully open and flexible tool, and that allows you to integrate controls algorithms to a certain plant model representing the system. And this can be done with native controls in GT Suite or with co-simulation to, for example, MathWorks Simulink. And in general, we have a flexible API that allows us to glue to many other commercial softwares and in-house codes. Now, when people ask, what is GT Suite software exactly, in terms of the different interfaces that we have inside the tool, it's probably best explained with a workflow starting from the left to the right, where we have a sequence of pre-processors, and that allows you to set up a model very easily, particularly with CAD data if you have it available. And then there's a main primary model building application called GTEs. That's our primary build interface. And then when you run the solver and things, you can analyze those results with a dedicated post-processor. So if we start on the left-hand side, you can see on the pre-processing, we have a CAD building tool called SpaceClaim integrated right into GT Suite. And SpaceClaim is actually owned by a third party called ANSYS. Many of you might be familiar with this. And so with every license of GT comes a license of SpaceClaim. Now, SpaceClaim is nice that it can help you clean up original CAD models. It can help you modify. It can help you extract fluid cores and structures and things like that and prepare it for a model simulation. Now, once you've got the native CAD model prepared, then you would bring that into our 3D preprocessor called Gem3D, and that allows you to take that raw CAD file and discretize that either into a fluid network, primarily in one dimension, or into a thermal network, either representing with a lumped node type model or with full 3D finite element capability. Or it could be taking that CAD model and discretizing it into a mechanical structure for mechanical dynamics and structural analysis. Now, in addition to these primary preprocessors, there are also other preprocessors we have glued to our GT Suite platform, including Converge Lite, which is a CFD software by Convergent Science. And a light version of this is included for free with a license of GT Suite. There's also Titherm, which allows for very sophisticated thermal analysis of different types of scenarios. And then finally, there's a Valvetrain design UI that's also included in GT Suite for IC engine, primarily Valvetrain type simulation. Now, once you have the model set up in a preprocessor, the workflow then would take you into this GTE's build interface, where you would export your discretized either flow model or thermal model or mechanical model into this GTE's interface. And then you would finish setting up your model by applying boundary conditions, running different trade studies, parameterizing the model to really focus in on things that you want to optimize or understand in more detail. And then once you have the model set up and just about ready to run, then there are things you could do either by running a built-in optimizer to find an optimum value of something, either with a single or a multi-objective. Or you can also run a big DOE, studying a large set of trades, and that can be on the order of tens or hundreds or thousands or even tens of thousands of cases to examine. Now, once the solver is called, it calls our multi-physics solver, which allows users to integrate at will different physical domains, including starting with fluid dynamics. Our solver is backed by a 1D Navier-Stokes solver that is two-phase capable and can also track species. And we'll get into a little bit more about what that means in a minute. But you can also integrate the fluid domain with a thermal domain, represented either with a lumped mass or 3D finite element approach. You can also integrate with mechanics for fluid structure interaction, for 1D to 3D multi-body dynamics, or 3D FEA as well. And then, as we're getting on the topic of electrified aircraft, and we'll be talking a little bit more about that later, is we have the ability to simulate simple and advanced motors, electric circuits, and also batteries, either at the electrical equivalent level or at the detailed electrochemistry level. Now, a lot of times these different physical systems need to be controlled. And so we have a built-in library for controls to study things like PID controllers, math equations, logic operations, and so forth. Or another alternative is to co-sim with MathWorks Simulink. Finally, we also have a built-in chemistry solver as well that allows simple equilibrium combustion to occur, or even do reacting flow with finite rate chemical kinetics. And then to round this out, we can co-simulate with other third-party tools as well. So when the solver is called, it could be doing any of those physical domains glued together or in isolation. Now, once the solver runs, then it launches our post-processing software here that allows you to really analyze and do powerful analysis right in the software itself. Now, in terms of thermal fluid modeling, the approach that we take is really with a transient Navier-Stokes solver that solves the same governing equations you would see with 3D CFD reduced down to 1D. And so what that means is we're solving for conservation of mass, momentum, energy, and species as well, using what's called the staggered grid approach, where scalar quantities like pressure and internal energy and so forth are solved at the center of every subvolume in the discretized network, and then vector quantities like mass flow and so forth are solved at the boundaries of these different flow volumes. Now, certain aerospace systems can be prone to interesting phenomenon like cavitation or boil off or two-phase flows and so forth. And so we're able to capture this by having multi-species support, but also for a single species, allowing it to change phase as well. Now, to further highlight the principle here, you can imagine, let's say you have a one-dimensional series of pipes here, and you can see the cross-section of the pipes sort of changing here, where you have a constant cross-section here in blue, and then it expands slowly. And depending on the length of the pipes that you have and the number of subvolumes that you've discretized it into, will calculate a unique pressure point, just like you would with 3D CFD, only in a much coarser scale, where you're resolving detailed wave dynamics, for example, and transient phenomenon. And so the flow can be either steady or unsteady. It doesn't really matter for the solver. And then finally, there are two different types of flow solvers that we have available. One is for short time scale type simulation, and another one for long time scales. That gives the user the flexibility to study different phenomenon very easily. Now, as I had mentioned, we are a flexible and open platform, and that allows us to glue to other software packages for co-simulation. And particularly if we look at controls type simulation, there is MathWorks is a very commonly used tool that we've been co-simulating with for many years. But if also for CFD simulation, there are many tools that we use gluing 3D CFD problems to 1D for transient boundary condition transfer. Now, on top of this, you can also write your own code, either in Python or C or MATLAB, and glue it right into a system model. And so here's an example of a user-defined Python function that's manipulating the model with user's own custom code. And then you can also do what's called model in the loop or software in the loop or hardware in the loop simulation, where ultimately what you could do is, instead of running a controller on a physical piece of hardware, you could replace that physical piece of hardware, which might be very expensive to test, with a virtual model inside GT Suite, where the physical controller is actually communicating with the model instead of the physical hardware, allowing users to save money by not having to test the physical hardware as much, and also allowing rapid development of controller algorithms and so forth. And then finally, our software is open with a generic API to link to just about any tool, whether if it's available, whether it's an in-house code or something that's non-standard. Okay, now I want to begin by talking about just a very simple overview to some of the various applications we see with aerospace systems. And so we'll begin by looking at environmental control systems. And so with environmental control systems that are commonly seen on aircraft and spacecraft, some of the key points to understand and analyze in these types of systems is to look at things like flow distribution and knowing, are you getting the right amount of mass flow to certain parts of the system? And so on an aircraft, for example, you might need to understand how much airflow are you getting to the cockpit versus different parts of the cabin and so forth. And so by building up an air distribution network with an ECS model, you can predict the mass flow distribution very easily, and you can see the breakdown, for example, of distribution to different parts of the system. Now, another challenge too is that noise considerations come into play, where velocities at any point in the system shouldn't really exceed a certain value. Otherwise, noise people might start to hear that and maybe be unsettled by it. And so you can check for things like velocity limits and so forth. Now, when building an ECS system, there are many components that go into that, including things like fans, heat exchangers, nozzles, valves, and so forth. And so these different components need to be hooked into the system, and all those components are certainly possible in GT Suite. Other things to mention here as well for ECS systems are things like humidity and temperature tracking. And so since the species is being conserved and energy is being conserved in the governing equations, we can track those things in a transient or steady state fashion. And then finally too, oftentimes for aircraft ECS systems, you'll see there are air cycle machines that provide the flow ultimately into the cabin of the aircraft. And so it's very easy to integrate an air cycle machine model to these ECS systems. I'm taking a deeper dive into the ECS system modeling. Oftentimes the workflow is quite nice where you can start from a native CAD model of the aircraft ECS system and the cabin, and you can discretize the flow path both through the piping in a one-dimensional fashion, but also of the cabin as well to do what we call kind of a core pseudo 3D analysis to look at preliminary temperature and flow distribution in a certain cabin environment. And so you can glue the 1D piping that leads into the cabin very easily with this 3D representation of the cabin itself to build a complete 1D 3D model that allows you to simulate things like pull down of an aircraft on a hot day, for example. Now, in terms of cabin modeling and the different approaches that could be taken in environmental control systems, there are a couple levels of detail that you could study. The first and probably the easiest method is to do a 0D approach to the environmental control system, where you have the detailed ducting that leads to different parts of the aircraft, and that can be connected to, for example, regions, including, say, the cockpit, which takes a 0D energy balance approach to calculate things like temperature and humidity breakdown in certain sections of the aircraft. Now, what's also interesting about this is that you can then take a control algorithm and implement this to see how you need to set up the controller to do things like regulation of cabin temperature, pressure, and humidity, and so forth. Now, for those that want to take a deeper dive, there's also the ability to do the coarse CFD representation of a given part of an aircraft inside GT. Or you can also, for more detailed thermal analysis, integrate with Titherm simulation for looking at things like detailed human mannequin modeling, where you can see, for example, what the temperature is of a certain part of someone's body at a given time or condition inside an aircraft. Now, with the ECS system for aircraft, oftentimes there's an air cycle machine that provides the boundary flow to the cabin itself. And the air cycle machine is a system all of its own, where there typically is some sort of engine bleed air or bleed air from somewhere that is the inlet boundary condition to this. And then there are a series of heat exchangers and turbo machinery that conditions the air and gets it ready to flow into the cabin. And so with the air cycle machine, you can study different parts of this at different stages throughout the machine, starting from, for example, the bleed air inlet condition, in this case looking at temperature distribution, all the way to the air cycle machine outlet condition. And in this case, it was examining the effect of, well, what happens if you have a dry air condition or a 50% relative humidity condition? How does the performance change? And so those types of studies can be done with the tool. Okay, the next sub-application that you can be studied are vapor compression systems. And another way of looking at this is an air conditioning system, or type of even similar types of closed network systems with refrigerants and so forth, or things like heat pumps and so on. And so the way this is simulated in GT is the various components of the vapor compression system, whether it be the compressor or the condenser or the evaporator and so forth, can be plugged in with detailed dimensions to predict the performance of the system itself. And let's take this example here of a helicopter with a 0D energy balance cabin approach, where the vapor compression loop here is providing cooling through the evaporator to the cabin. And so you can examine things like cabin temperature and pull down as a function of time for VCS type systems. Now, this is a fully transient scenario, but it also handles zero flow as well And so, for example, if the compressor is turning on or off, sudden changes in the mass flow, the solver can still be quite stable in these scenarios. Now, transitioning to the fuel systems application, users can build up an entire network for modeling a complete fuel system of an aircraft, all the way from the boundary condition of the tanks and going into different feed lines that ultimately feed fuel into the engine of the aircraft. And so using model inputs like the tank geometry itself, either with a simple approach or a 3D approach, and specifying initial conditions like initial level of fill of the tank, and then including different components like pumps and valves and so forth, and feeding boundary conditions, the user can then study for example, volumes inside a fuel tank over a flight mission. And so that's one of the things that can be studied, but also looking at fuel transfer, weight and CG in a transient fashion, the filling and venting, or if there's inerting of these tanks with OBIGs phenomenon, the OBIG system itself could be studied. And then also thermal considerations could be taken into account, including flammability, freezing, and spillage, and so forth. In terms of the detailed 3D tank modeling, there is the ability to take original 3D CAD and then simulate to find the free surface fill level of a tank at any given arbitrary orientation. And so this has a nice advantages to simulating these effects, to look at things like filling scenarios, venting scenarios to know if it's well vented or not, and fuel transfer phenomenon, and pickup locations for fuel pumps under a variety of different orientations of the aircraft. And so by predicting this with virtual simulation, this eliminates, reduces anyway, the need for strenuous physical testing. Transitioning to turbofans and turbojets, turboprops, and IC engine systems, the user could study many of these different types of power plants in GT Suite, starting with typical IC engines that you might see on lighter duty aircraft, where the user can build the entire engine breathing system to predict performance under different conditions, particularly taking things into account like altitude and fuel composition and so forth, to investigate performance under those types of conditions. Additionally, the users can build things like turbojets or turbofans to look at the primary flow path, and this utilizes either our equilibrium combustion library or the kinetic chemistry library to build a detailed performance model in GT. Now, we also realize that for turbojets, turbofan type propulsion simulation, that the tool by NPSS is also widely used in the industry. And so we have ways of gluing with that tool to look at surrounding systems to the engine to do co-simulation in that type of form. The next sub-application that could be examined are things like landing gear analysis and detailed hydraulic systems. And so, for example, looking at landing gear retraction and extension type events, looking at hydraulic pressures and valve behavior and so forth, you could build up a detailed hydraulic network to study those types of effects. And then for detailed landing gear design, the design of the Oleo strut, for example, is of interesting importance. And so users could parameterize different parts of the landing gear to hone in on optimum designs. As you can see in these animations here, it's set up in the rather extreme case for a bad scenario where if you're doing a standard drop test, you get some nasty vibration here after the original bounce. But honing in on an optimum design, particularly of the valve behavior in the Oleo strut, that allows you to really achieve the optimum damping characteristics, so you get a nice smooth landing in a drop test. Now for hydraulic systems, this also extends to flight actuators, but also things like fuel pump analysis and looking at detailed predictive pump analysis, or fuel pump metering units, and engine fuel feed systems, and so forth. Advancing now to the electric and hybrid powertrain, there are different concepts that could be explored inside the GT Suite modeling tool. And this allows users to explore different electrified concepts, whether it's looking at a pure eVTOL type scenario where you're looking at different battery arrangements and motor layouts and so forth. But there's also different types of hybrid approaches where you could have a gas turbine along with a battery and connecting to a certain propulsion system. Or you can also look at things like electrically driven air cycle machines or fuel cells as well. Now, in terms of batteries, we realize these are becoming more popular, particularly for eVTOL aircraft and so forth. That for batteries specifically, there are detailed levels of analysis that could be studied in GT Suite, including the ability to do electrochemistry. And so that allows you to predict the performance of the battery instead of necessarily relying on a map, an electrical equivalent map from test data or from the supplier. And so with a predictive model, that allows you to predict the state of charge over a flight mission, for example. But it also allows you to predict aging characteristics and the state of health of the battery over time to see and allow the users to, for example, optimize the state of health to get the battery to last as long as possible. Now, this also leads into the coupled influence of thermal behavior. And so by having different thermal management strategies on batteries and so forth, that allows you to really examine what might be the proper thermal management strategy for a given battery setup. Now, additionally, thermal runaway considerations could be considered, where you investigate an entire battery pack, and you, for example, blow up one cell or heat it up enough to where it will blow up, and see what happens to the rest of the battery pack to see if it will actually propagate or not. And so thermal runaway physical testing can be very expensive and very hard to examine all of the potential avenues that could lead to thermal runaway. And by having a simulation approach to this can really save a lot of time and a lot of physical testing. Now, finally, as it relates to electric and hybrid powertrain, there's the ability to look in detail for e-component thermal management. And so, for example, for batteries, you might have a stack of batteries that you're cooling, and you want to see the cooling distribution along a battery pack, for example. Or with electric motors, the users can look at electric motors from a thermal analysis to make sure that the motor doesn't overheat under different operating conditions. And just to look at an example case study that was done, there was a joint paper that we did last year with Airbus's A-Cubed division at the AIAA conference, looking at one of their Vahana aircraft, which has 8 electric motors, and you can kind of see the layout here of what the aircraft looks like. And one of the goals of the study here was to analyze pack thermal performance over a flight mission profile, and also examine state of charge of the battery pack. And here you can see just an example correlation, which is in quite good agreement with testing, where we're looking at temperatures at different locations in the battery pack over a flight mission profile. Now, there's other scenarios that this could lead to, including examining, well, what happens if we put in a cell into given thermal runaway, or basically blow up one cell? Does that lead to thermal runaway inside the pack, or is it isolated enough to not be a problem. And then also, this could also lend itself to state of health monitoring, taking into account different mission profiling, where you might discharge over a given notional flight mission profile and then recharge a battery at a given C rate and then rest and so forth. And depending on the cycle profile that you put in, that can determine how long your battery will last, and then what type of thermal management strategy would you need to have the battery last as long as possible. Another type of electrified powertrain concept is with fuel cell study that was done by NASA, which presented at our user conference a few years back, where it was examining PEM type fuel cell to study electrical, chemical performance, but also cooling system performance to make sure that the cooling system is working properly. And here you can see there was a comparison to the electrochemical performance, looking at stack voltage inside the fuel cell, and then also looking at cooling temperature as a function of time as well. And so here you can see a schematic of the model that has a fuel cell inside, but also a surrounding cooling system, and then the fuel and the oxygen supply that ultimately converts this to electricity and power and so forth. Now, switching gears here to talk about space propulsion systems, there's a variety of different thermal fluid analysis that can be done in the area of space propulsion. And this includes concepts of looking at, for example, fuel and oxidizer feed system lines leading to rocket thrusters. And that includes the ability to put in components like heat exchangers, turbo pumps, valves, and so forth. And also the user can look at combustion inside the rocket thruster using either our equilibrium combustion model or finite rate chemical kinetics. And here you can see an example of such a system, starting with the LOX tank and the liquid hydrogen tanks leading all the way down to the rocket burner itself. Other types of systems that can be studied include helium pressurization systems, but also water hammer and surge analysis to protect sensitive components in a feed system line. But in addition to that, there's tanks that are carrying the fuel and oxidizer, and it's important to understand the thermal behavior of these tanks to ensure the fluid inside the tanks is well conditioned and not leading to boil off and so forth. And then other types of scenarios include line chill down, ground support systems, and so on. So just to show a case study here is looking at, there's a nice water hammer case study that was done by Penn State at last year's AIAA conference that looked at the typical scenarios that you might see in a space propulsion system, where you suddenly open up a valve to a thruster, and you want to see what the peak pressure might be during an event like that. And so there's some well-documented test studies that are available in literature, and also with the test lab at Penn State. And GT Suite was used to study those different experiments. And you can see there's pretty good agreement between GT and testing, for example, analyzing peak pressures in a given line. And then by looking at these peak pressures, then the user can then rate different components to ensure that they can withstand these types of pressures, or redesign the system to minimize that pressure as much as possible. And oftentimes, sticking with the space propulsion feed line system analysis, one way to dampen those large pressure spikes that you might see in such a water hammer event is to have a venturi somewhere inside the line. And GT has a sort of a novel approach to studying cavitating venturis, where the user can discretize the line itself into many small 1D cells, and that allows the user to predict the pressure distribution inside the Venturi itself. Now, the Venturi, if can be done in a predictive fashion like this, and you can see there's good agreement between GT and 3D CFD models out there. So, for example, with ANSYS Fluent. But we've also compared this predictive approach to test data that's available for a variety of different upstream pressures and so forth to give a truly predictive solution. But the user can also, for system level modeling approach, can also characterize it either in a non-predictive manner as well. And then another case study is looking at the realm of tank thermal stratification. And there was a study done back in 2018 at the NASA TFOS conference, which examines the effect of tank thermal stratification and its effect on boil-off behavior inside the tank. And so by utilizing the fluid elements inside the tank, discretized into many axial discretized cells, that can be integrated with the thermal structure representing the walls of the tank and the thermal fluid interaction with heat transfer in between can study and ultimately analyze thermal distribution along not only the tank walls, as you can see in this schematic here, but also detailed thermal behavior in both the ullage and the liquid inside the tank. And then finally, to round this out is also a very nice case study that was done at a users conference by GT a few years back. And this study was done by Roush on a ULA IVF system. And this really combines many different components of an IVF system together, where it's starting from the tanks, the liquid hydrogen and oxygen tanks, and then flowing those ultimately to an IC engine to generate electrical power and so forth, and also helps reduce the need for helium on board aircraft. So the IVF system itself is an interesting forward-thinking type technology, but it encompasses the different multi-physics capabilities inside GT, where you have the fluid behavior being modeled all the way from the tanks to the engine. You have combustion inside the engine itself. You have heat exchange to heat exchangers. So there's thermal analysis going on there as well. You also have controls and so forth. And so it's a pretty interesting scenario that can be studied. And finally, to round this out, is the ability to integrate different subsystems together. And so similar to that IVF study that was done, we're combining fluids and thermal and combustion and so forth. The analysis here could be analyzing subsystems that are glued together to do complete virtual integrated aircraft. And so this is a common theme that we see in the industry, is the desire to want to glue different subsystems together to really understand complete aircraft total system performance together. And so one such example here is looking at just 2 or 3 subsystems of an aircraft, where you have today's modern aircraft require more cooling of electronics and so forth. Electrical loads are getting only higher as more aircraft are being produced. And so you need to cool those electric loads. In this case, where a vapor cycle system was being used to cool down an electronics cooling bay. And the heat that's ultimately generated from these electronics is basically being transferred from the vapor cycle system and dumped into a fuel system to act as a heat sink from the electronics loads. And so in this model, it's combining both the thermal behavior of the electronics itself and the 2-phase behavior of the vapor cycle system, and then the single-phase fuel hydraulic system. And then there's also the ability to co-simulate with Simulink, as you can see in this example, or you could also think of using existing homegrown tools to do this as well, where you're controlling different aspects of the model with an external code. Now this study, if you want more details about it, you can see there's a study It was published in SAE magazine back in 2017. With that, hopefully gives a nice overview of the different capabilities we have for a variety of different subsystems on aircraft systems and spacecraft systems. Now I'd like to jump in and show a live demonstration of the software. And so if I go in here, I'm just going to open up our primary model building interface here. And I first want to start by showing the typical model map. The way it looks is the physical system that the user is trying to build would be located in this region here. And then these systems would be built from templates from what we call our template library. And this is divided into different physical domains, whether it be fluid flow or mechanics or thermal, electromagnetic controls, and so forth. And so the idea or the concept here is if you were trying to build a model from scratch, you might say, okay, well, my model has a pipe in it. I'd go in here to this template library and search, for example, pipe. And then it shows you a breakdown of all the different components. And then, for example, if I find the component I want, then drag it on the map, and then describe the inputs, the geometric inputs that go into building this particular component. In this case, a round pipe. Once you go in and you fill out the details, then you go in and you just keep selecting components. Let's say you want to model a valve. You go in here, you type valve. We've got a bunch of different ways of modeling a valve. Let's just say I want to go and add a check valve into the model. I go in and then you can start linking these components up to build whatever system you want. So that's kind of the concept behind building a model from scratch. Now we have many different examples and tutorials and manuals inside the software pre-built. And so if you go to the File menu under Examples here, you'll see under the Aerospace section, we have some canned examples that give you a flavor for modeling different types of aerospace subsystems. In this case, we're opening up a typical type of fuel system, and a lot of the components you might see in a fuel system of an aircraft, starting from different 3D tanks to looking at things like boost pumps and ejector pumps, heat exchangers, valves, and so forth, can all be stitched together. But there's also other types of components and subsystems in here as well, including environmental control systems, vapor compression systems, air cycle machines, cryogenic systems, also for jet engines and landing gear systems as well. And so, for example, if we go into this ECS ducting example, this is another one that's already kind of pre-built for the user to give an idea of the types of components that are required to build a subsystem model like this. Now these models can either be built by hand by the user by taking elements from our template library, but another very common workflow is to rely on 3D CAD data if it's available. And so when that is available, the user can go into the GEM 3D preprocessor and import a CAD model and discretize into a system. And so I happen to have GEM 3D pulled up right here. And under GEM 3D, you can see there are also examples here. And if we go to the Aerospace systems, I can pull in some examples here. So for example, this ECS ducting model will go through and show as if the user had imported the system model from CAD and then gone in and discretized this into different chunks and so forth to build a 1D flow network directly from the CAD. And so when you go to Export GT Model and you hit Export, once it's all discretized, and we'll be showing this in a later section on ECS modeling in particular. If you hit the Export button, then what it does is it generates many flow volumes behind the scenes and ultimately builds a model map that you would see something very similar to this here. And so once it's gone through and it's hooked everything together, you hit the Open in GTEs button, and then you can see, for example, the different components that are stitched together to represent this system. And then finally, when the model runs, you can see some of these examples here are already pre-built. You can see in our case setup here, the user can explore different cases and trade studies very easily inside the case setup to say, okay, what happens on a hot day or a cold day or at altitude? You can change those scenarios very easily here. Now this model has already been run, but if you wanted to run it from scratch, you just hit the run button to launch the solver. And then once the solver completes, you would then view these results. And this model has already been run, so we're going to just quickly show the post-processor here, where you can go in after a model has been run. You can go into any component. Let's say, for example, there's a cabin temperature controller here. You could look at things like performance of a PID controller. You can look at clicking on any flow volume, things like pressure, temperature, and so forth as a function of time. Or for steady problems, you can also look at things like averages and minimums and maximums as well. And then one more added advantage is that if you're building models from 3 dimensions, 3D CAD, you can then overlay visual results right on top of the original 3D CAD. And so, for example, we're looking at, in this case, pressure distribution inside the ducting of the ECS system. And so the post-processor is really powerful. This is just showing you a snapshot inside the post-processor. There's many more capabilities of this that we can show if you check out some of our other video tutorials and attend some trainings. Now, with that, I want to close this out and mention that we have various ways of getting you up to speed with the tool. And the first way is that we have unrivaled technical support that's included free with the license. And we take great pride in our technical support. We have many experts in-house that work one-on-one with our customers to ensure that they're getting the confidence they need to build their models and get them running right, and validating to test data, and ultimately predicting trends that will save both time and speed to market for different products. And now there's also free one-day trainings that we offer once a month at our local offices in Illinois and Germany and India. But as you saw in the demonstration here, we also have many examples and tutorials and webinars available for you as well. Also know you're not starting from scratch. We can build baseline models for you. We're happy to work side by side with our customers. And also know that custom on-site training is also available. With that, I want to thank you very much for watching. Please visit our website at gtisoft.com or search for other videos on our website or YouTube. And if you have any questions, please do not hesitate to contact support@gtisoft.com. Thank you very much for watching.